Thank you everyone for joining us for the inaugural Colloquium speaker. Today we have Lei Li, who is a new associate professor here at the LTI. So Lei comes to us with a wide variety of academic and industrial credentials, and today he'll be talking to us about empowering responsible use of large language models. So Lei, please.
Yeah. Thank you. Correction, assistant professor.
Oh, sorry.
Yeah. Thank you, Fernando, for the introduction. I'm Lei Li. I just joined literally 1 week ago, 2 weeks ago. Yeah. So I'm working on machine translation, large language model, and text generation. Today, this talk will be more about the responsible part and trustworthy part of the large language model. So I'm sure many of you perhaps have already used large language model, ChatGPT, Bard, or more recently Claudia 2, which are great. Perhaps some of you even played with the model itself, like the open source version, Llama, Alpaca, Vacuna, etc. So I also used ChatGPT to create something funny. So, well, I asked ChatGPT to create a tweet for my talk today, and this is generation. Well, I don't even know, like Pittsburgh, they call themselves Yinzers. Okay, that's fun to know. And I do hope my watermark scheme, AI detective skills can be more sharpener than pure gray. So, well, I don't know. That's very sharp. So what's the power or secret source of this ChatGPT and all these large language model? So this is actually built on top of a very simple task. Probably everyone in the room in your childhood you can do just to guess what's the next word. For example, I was at Santa Barbara before. So Santa Barbara has very nice, well, we have nice beach, nice weather, nice sunshine. We don't have snow. Well, Pittsburgh is the city of bridge. So we have a lot of bridges. So this is very easy to do, but we want to do that with a neural network. We use a very deep neural network to predict the next word given the prefix. And once we combine them, we can do amazing generations, word by word. So what's special about ChatGPT? Well, ChatGPT is using exactly the same framework of this neural language modeling to predict the next word token, but it's trained on very large number of corpus, 300 billion tokens, with a small amount of human feedback. It's able to do prompting, so you can guide the model through natural language instruction. You can also provide a few small examples to tell how to label the data, how to predict the data through this in-context learning. And it's able to generalize to many new tasks that it has never seen before. So that's amazing. But however, large language model can also be used for malicious purpose to generate fake news, fraud, scams, etc. An earlier case from New York, so a lawyer actually used ChatGPT to create 6 fake cases. They look like real, but they are not actual real cases, and they use this in the court. And this lawyer is fined because of that. And also, students tend to use ChatGPT for their assignments and papers. It's hard to detect. So an important task for us as professors, we have to figure out ways how to identify the homework, these papers, whether they are written by students or they are generated by this large language model. So it's hard to do. And it's actually very easy to misuse ChatGPT if you don't know about the mechanism of ChatGPT. So this is a real story. A professor from Texas University, he just used ChatGPT to tell whether the essay is written by ChatGPT or actually written by a human. So, well, apparently they made a wrong prediction. And it's very harmful, it's very dangerous. But there are other dangers as well. This pre-trained large language model can contain and leak private information such as phone number, email address, even your social security number, even if you just train that from the public data. There are other issues like copyright. There's an attack method called a model extraction attack, which is to extract model information by querying the model in black box setting. So in this way, the attacker will be copy and distill from the model, and then use it to train their own student model. There's also unsafe generation. People use the GPT-3 to give medical advice, where sometimes it can give very dangerous advice. So I also have a personal story. Even as an expert on large language model myself, I can make mistake. So I used this ChatGPT to calculate the number of late days for a course I taught in the spring. So my TA just used that. And where there are many students, we can't verify all of them. We just verify a few of them. It's right, it's correct. So we just assumed the whole thing is correct until we got a complaint from one student that was wrong. So you can mess up. So in today's talk, I'm going to talk about two aspects of responsibility and trustworthiness of large language model. The first one is to detect AI-generated text. The second one is to add a watermark to the model so that we can protect the model from being stolen through distillation. Okay, let's start from the first one. So here's a piece of essay. Can you tell whether it's generated by human or generated by chatbot? Well, it's very difficult to tell. It's actually a Turing test. So what should we do? Well, we can train a machine learning model to predict and to try to solve this Turing test. Well, in order to do that, we need a lot of data. And even if we have a lot of data, it doesn't guarantee high accuracy. So here are some of the models developed by prior research. All these models on the right, I'm showing the false prediction rate. It can make errors. So all these classifier-based models, they can have both false positive and false negative as well. So how should we handle this? How can we guarantee the prediction? Well, one solution idea is to add a watermark. Actually, this is what we do for image. We can just add this visible or even invisible watermark. It turns out that image watermarking has a very rich history. So people studied various ways to add a watermark. So this is one particular way that to add the semantic watermark, you won't be able to see on the original image showing here on the left. But if you do some signal processing, there are some patterns here on the right. And clearly, there are some semantics there. So that's good. But what about text? Can we add similar watermarks to the text so that we can protect the text, or we are able to identify whether this piece of text is generated by model or created by human? Well, let's try. A very simple idea is we directly add some special words and phrases where we can just literally add this copyright notice here. But it's not robust. So you can simply remove that text from original text. Let's try another way. So can you tell what's the watermark here? But this is generated by ChatGPT. I just asked ChatGPT to generate this piece of text. Well, if you look at the first letter of each line, so you will recover that. That's Pittsburgh. But again, this kind of watermark, you can just replace some of the tokens. If you identify the particular secret message in the text, it's easy to remove. So watermark the digital text, it's challenging. But the problem is we really want to put some subtle signal into the text itself, so you won't be able to notice it. But there is a way. Later, you can determine with some algorithm, you will be able to identify the particular secret message. So this watermark approach is different from the classified prediction approach. In watermark, we really want to prove that this piece of text is generated by AI. Not just by AI, but we can actually prove this piece of text is generated by a particular model used by a particular user. Classifier-based, that's to predict. So prediction versus a proof, it's different. Well, what do we need for a high-quality watermark? So we need to have a set of property to ensure this watermark actually works. First of all, we want to make sure adding watermark won't make our generated text worse. So we want to retain the quality of the generated text. And we also want detection guarantee. We don't want to make false positive or false negative. So we don't want to miscatch any AI-generated text, but we don't want to wrongly, incorrectly classify human-reading ones as well. Another very important property is security property or robustness. There are all possible ways to evade the attack. For example, people won't just use the text directly generated by ChatGPT. People will modify, will crop, will shuffle things, will replace some of the words or paraphrasing. So even with those attacks, our watermark should remain there. It should be robust to those attacks. So how to do that? How to achieve that? Let's revisit the language model. So in language model, we want to predict the probability of next word given the prompt and the prefix. So here's the example. So Santa Barbara has nice, we have a list of tokens from the vocabulary, and our model will tell the logits for each one, and then we normalize these logits, we get the probability. And then we can perform decoding algorithm. We can do Bing search or just the sampling. So our key idea here is we want to bias the probability a little bit so that the secret signal is added to this probability. We propose this method called GPT watermark. We will still use a model the base model to generate the probability. But before generating the logic and probability for each of the token, we will first randomly split the tokens and words into two groups. One is green list, the other is a red list. So this is purely random based on a hash function. And now we generate candidates for next token. We will generate words from green list. It can be from red list as well. So from the model itself, we will produce these logics for each of the token. And for every token in the green list, we just add additional small information here, additional data here to the logic itself. So that's before the normalization. Once we've done that, we normalize the probability again. We get the updated, modified probability. And then we decode with that probability. We can either sample from the probability or we do bin search from the probability. So in this way, essentially, we're increasing the probability of all green tokens slightly with this data and decrease the probability of all red tokens slightly. Okay, so hopefully this slight change won't affect the quality of generation. And we will be able to detect such small amount of information later. So formally, here's the algorithm. So we use a hash function to hash the vocabulary into green list and red list. And then we apply the language model to all tokens in the vocabulary and to compute the logics. It can be applied to any language model we have. And then we modify these logics before computing the softmax. And then just a normal decoding. So that's the full algorithm. It's pretty straightforward. How we detect? So detection is actually counting. So suppose we have a suspect text here, Y. We have a sequence of tokens now. We just compute this z-score based on this formula, where inside this formula, essentially, we're counting the number of green tokens in the output text Y. Once we have that, we can set a threshold. If it's greater than a predefined threshold, then it's watermarked from our model. Otherwise, it's not watermarked. So it's pretty simple. It's very fast, very efficient. And let's see one real case, what really happens behind the scene. So suppose I have this prompt, and I have original generation. So we are using a Llama 30 billion model to generate this piece of text. For every token, I marked either in green or red. Because we randomly split the tokens into red or green, so normally you will see 50-50 split among the generation. Now, after watermark, because we slightly modify the probability, so now after watermark, we generate again. And if we count the number of tokens in green and in red, now more tokens are from green list. significantly more. So if we compute their z-score, so z-score from this watermarked is much larger, much greater than the unwatermarked z-score. So there's a clear difference. So one benefit or advantage of our GPT watermark, it comes with mathematical guarantees on the quality. We can ensure that this watermarked large language model and original large language model are indistinguishable. So I will talk in a minute what do we mean by indistinguishable. And we have guarantee of false positive rate and false negative rate. It will approach zero exponentially as number of tokens increases. And it's also robust to edits. It's twice as robust as recent notable baseline in ICMR from Tom Gushtin's group at the University of Maryland. So about the quality guarantee, we can use a notion called Renyi divergence. It's a generalized notion of KL divergence. Actually, if we use a particular choice of this alpha, we get the KL divergence. So we can prove that this KL divergence between the watermarked and unwatermarked probability is smaller than some threshold, which is determined by the amount of information we add. So essentially the data we add to the probability. So essentially that means our watermarked, showing here in red, watermarked language model won't be too much different from the original language model. So, well, is that true? That's theoretical. So we did some experiments on GPT-2, OPT, and Llama, all these large language model with different size. So this one is the perplexity of the generated text. So lower is better. We have this blue bar is corresponding to human written ones. They are high quality, and we have three different baseline. We have unwatermarked generation from the large language model itself in orange, and green one is a previous baseline and our one. So our red one is very close to the prior generation and also the unwatermarked one. We also annotate the text quality, and so human evaluation of the quality is actually confirmed that this watermarked one and unwatermarked one have similar distribution of the human reading. We also prove that this GPT watermark is robust to edits. But in order to quantify that, we need to quantify the amount of effort for the edits. Of course, if a human just replace every word from the GPT generation, so the text will be completely changed, so you can actually remove the watermark completely. But if we set a limit with an amount of effort by human, and by number of edits, like quantified by the edit distance. If we set the upper limit of that, then we can quantify this adversarial robustness. So it will be robust if people, human, just make a small number of edits to the text. So the watermark will remain there. We are still able to detect such watermark. So that really means, well, if the student use ChatGPT to generate the assignment or essays unless they really spend a lot of effort in rewriting the whole thing from ChatGPT, where we will still be able to catch that. What about the detection rate? So this is empirical evidence of the z-score we calculated for various models. On the left group here, this is watermarked, and the second group are unwatermarked and then human. So unwatermarked and human, they have similar distribution in terms of the z-score, while watermarked has a clear difference from the other two groups. So this really implies that we are able to detect such watermark easily. So I have two additional remarks on this watermark. Does it work for all types of generation? There are some assumptions we really need to make about the generation. We want the generation to be natural and diverse text. So if there are some generations that's really not natural or not diverse at all, like with, for example, this case, it's actually difficult to add a watermark. So that's one remaining challenge. We're still working on that for this low entropy text generation. Another assumption we need to make is we assume this homophily condition for the token probability. So essentially, we assume that the probability of next token in the green list or red list, they are homogeneous across time. So they won't change too much over time. Of course, there are certain situations this could change. For example, if you have really long dependency, long-range dependency, that well, this long dependency is special. It's not just on the word level dependency, but this kind of dependency essentially will limit your choice of the word. Essentially, in the end, you will find, okay, you can only generate the words from green list, from one group of the tokens. Then if such things happen, then that will destroy the watermark. Essentially, if we add a watermark, either we will get some text that's unnatural, or we can't add a watermark at all. I do want to mention that our work is related to an earlier work in ICML this year, Kirchenbauer's work on watermark. And their watermark scheme is very similar. They also have this green list and the red list split. The difference is their green list and red list split is dependent on the prefix. Therefore, it's more complex to analyze the theoretical guarantee. And because we have homogeneous green list and red list, we can achieve better theoretical guarantee than their method. So what about attack? Well, I talked about several ways to actually attack this watermark scheme. One particular and strong attack is paraphrasing attack. We can actually use multiple ways to paraphrase and trying to remove such watermark from the text. For example, we can just use ChatGPT itself, try to paraphrase the generation using ChatGPT, or we use a dedicated paraphrasing model such as Diaper developed earlier. Or we use some summarization model. For example, BAT, we just summarize the text, and sometimes it's rewriting the text. So, this this potentially could remove the watermark. Well, we did some study on data set, on real data set, and we can still show empirical, even if you have paraphrasing methods, various paraphrasing methods, our model, our method is still able to retain this watermark and to robustly identify the watermark after paraphrase. Another important question is where our method falsely detect human written ones. So we did a study on a set, a TOEFL data set. Those are essays written by students, and they are really generated by students rather than generated by AI. Comparing to all the prior approach, all the rest method are prior classifier-based approach. All these methods will have false positive, while our method, we have 0 false positive. So a quick summary for this part. We devised a rigorous theoretical framework to quantify the performance drop after applying the watermark, and the correctness of the detection, and security guarantee against editing attacks. And it's probably robust and empirically verified. So that's for detecting AI-generated text. So for the remaining minutes, I will talk about another security aspect of the large language model. While I was working at ByteDance before, we deploy our machine translation model online. We always had this fear that some of our clients may potentially just use our API to query enough example from the API, and then use that queried example to train their own student model. So this is known as model extraction attack. Of course, we want to protect our intellectual property. We want to ensure the fair use, where we don't want our client to just steal from our model. So how to prevent that? Well, our key idea is, again, we want to add some watermark to the model. But here, the difference from the first project is we want to add such watermark to the model so that even after distillation, the student will carry such watermark. Then later, if we detect, identify or detect such signal from the student model, we will still be able to recover such watermark from the student. Then we will be able to tell whether this model is distilled from our model. So this is particularly useful for any model owner, developer organizations who wants to prevent the model being misused. So how to achieve that? I will start from a simple model. So this is a classification model. I will talk about the generation model later. So for this classification model, suppose we are just using BERT. So this model will tell the sentiment of this statement, just positive or negative. So we use this model, we call it a victim model, where we want to, adversary want to distill from. Now we compute the probability of the positive class given the input. Once we have that, we add some watermark here. so that we can bias the probability of this positive class in a way that's corresponding to a particular frequency of sinusoidal signal. So this sinusoidal signal, this frequency, is the watermark we added to the model probability. So that's the key idea. And hopefully, after we add this, if the adversary trying to distill from this model, their student will carry such frequency in their student model. They don't know because the way we organize the input, we hash all the text into uniformly into a linear line. And this hashing is determined by a secret we just keep ourselves. So that's the key idea. And how about generation? Well, generation turns out to be slightly more difficult because we do have open vocabulary. We have many categories to generate. So we have a vocabulary here. And again, we use a hash function to randomly split this vocabulary into two groups. We have group 1 and group 2. And we have another hash function that will map any input sequence uniformly into a 0-1 range. So that's very important because later we will use this hash function to recover the signal. So now we need to generate. So now adversary is trying to generate. So how we provide this signal? We have the input, we have the victim model, we compute the language model probability, we have the original probability here. And next step is we use this hashed value to compute a secret sinusoid watermark, and we add such watermark to the probability for group 1. For all the tokens in group 1, we just proportionally increase or decrease, depending on the value we get, the probability here. And in the meanwhile, we will change the group probability for the second group as well. Once we have that, our probability for group 1 and group 2, they are slightly modified. And then we just decode with normal decoding algorithm. We can use bin search, we can use diverse bin search or sampling, whatever decoding algorithm we want to add. Then student will get the probability from this. They can either get the probability or they just directly get the output text. They use that to train their own model. So how about detection? Well, at detection time, we have a suspect model. So since we know we have the secret key, we know how to hash all the input into this linear line, we just provide a set. We call it a probing set. This is a set of input to probe the suspect model. And we get the probability or their output from the suspect model. And then we use Fourier transform to identify the spectrum in the frequency domain. So if it's actually distilled from our watermarked model, we will see such spike in the particular frequency corresponding to our secret. So we will see these huge spikes here. Then we will be able to tell, well, does it work in practice? Can we retain such a signal in the student model even after distillation? So here's one example. So this is one negative example. The original model probability is showing here in black. So that's a signal we add to the original language model probability because we explicitly add that. It has such a sinusoid signal. It's very clear. And these orange dots are actually the prediction probability for the tokens. But this model is not actually distilled from our watermark model. So this is actually a negative example. So if we analyze their frequency here, we don't see a particular spike. There are a lot of spikes, but they don't have a unique spike. So this is another example. This is a positive example. The same original watermarked probability here. We are probing a model that's actually distilled from our watermarked model. So from the orange dots here, we can't really see. It's a mess. We can't really tell. But if we analyze them in the frequency domain, there's a clear spike. The spike is corresponding to our secret frequency. So we can tell in this case it's actually distilled from our model. Well, it's not just the detection. We analyze the quality of generation. We are using machine translation and text generation model here for WMT, IWST, and IOC stories. This is a story generation. On the top are generation quality in terms of blue score or rouge score. So the higher, the better. The first one, blue bars in each group are original model. Those are where they are high quality. And then the three remaining ones are corresponding to different watermark mechanism. The last one is ours. So we really want to show this watermark. After watermark, the quality doesn't degrade much from the original unwatermarked model. And on the bottom, this one shows the detection rate. So we have much higher detection rate than prior approach. Okay, so let me quickly summarize the watermark. What we want to achieve is we want to add a watermark to the model so that this watermark will be kept even after distillation. So it's so these two methods, DRW and Jingsu, these two methods, they are general. They can be applied to any language model or text generation model or machine translation model. They are flexible. If you get the probability from the student model, that's better because you can use that probability. If you don't get the probability, if you just have the hard-labeled output from the student, it's slightly more difficult, but we still be able to identify that watermark. And it's effective and scalable as well for end user. I don't want to mention that there are other types of watermark scheme. So this watermark is a really hot topic, in particular this year after ChatGPT. So if you are interested, I highly encourage you to check out all these different watermark. There are a couple of final thoughts on the trustworthiness and responsible large language model. So these large language models are very powerful, but we do want to ensure responsible use. We want to ensure there's fair use, ensure the authenticity of the created content. We want to protect the intellectual property, copyright, protect the privacy. I didn't talk about the privacy in this talk, but we do have some work on protecting the privacy of the trained large language model and the safety of the generation as well. Of course, this is just the beginning of the area. There are a lot of remaining challenges. And I'd like to mention a couple of possible directions. One challenge is we do see a little bit of drop in the watermarked model in the distillation case. So if we add the watermark to the model, then the watermark model basically will drop a little bit in terms of quality. So how can we reduce that quality drop? And I also mentioned this low entropy text. For example, if you generate code, where software code, they have a very small set of vocabulary. So it's probably a low entropy. Adding watermark to that type of text will be extremely challenging, but not completely impossible. And other stronger adversary attacks. I mentioned that we can get stronger theoretical guarantee in terms of the detection rate and the robustness. But there's one issue. Since we use homogeneous green list, red list across a number of timestamps, these green list and the red list, they can be guessed by adversary. So if you know this green list, red list split, are we still be able to protect the watermark? When we have some partial answer, we don't have complete answer yet. Again, if in other cases, if we have other ways to guess the hash function, guess the secret key, can we prevent that even if the adversary knows that? We probably need something like public private key, so that we have some public key. Anybody can use that to protect, but we have some private key, only a particular person can identify that, or vice versa. Other attacks like the mixed fine-tuning. So for the distillation case, we just assume our adversary will query our model and use all the text, all the synthetic generation from the victim model to train their own student model. But maybe that's not the case in practice. Adversary will be smart. They will use a part of the queried data, and then they will have their own data or some other additional public data. They combine all these data together to train. Or maybe they query from multiple models. They query from ChatGPT, from Llama, from other models, and combine all these multiple generation. Even if you have individual watermark for each one, after you mix them, the signal can be mixed. Then it's difficult to identify such watermark signal. So these are all challenges. I just want to emphasize it's a great time, very exciting time to work on this. And a lot needs to be done in responsible large language model. Of course, this won't be accomplished without my excellent students and collaborator, Xuandong, Kexun, Pavendra, and Yuxiang, who is also a graduate of CMU. So we do have other works on the privacy for large language model, and also watermark for other type of data like image. So feel free to check out. That's all for my talk. Any question?
Other questions from the audience? Yes, please.
I'm curious how you would define responsible AI. I always find this term kind of interesting because it sort of implies that people, what does that mean about the other kinds
Great question. Well, probably Professor Mona, our head, has a better answer, like responsible thinking. I think this is along that line. Of course, it's very broad. There are many topics. So my talk only covers two particular aspects. So we want to identify whether it's AI-generated text or not. So we want to ensure that this AI technology is used in a reasonable way. So, students perhaps don't use ChatGPT for homework writing.
I appreciate the many methods that you propose to protect the models currently have, identify the text generated by these models, maybe correctly. But what do you think, like, in future generations, when we want to train the models, there will be a large portion of the data generated by the model. And would these watermark techniques help us or prevent us from identifying those when we make the data?
Great question. So let me try to rephrase your question. So if in the future a lot of data are generated by this AI model, and we use that generated data to train future model, so would that affect the model? Yes, that will affect the model, of course. So one solution, possible solution, is related to a line of research called membership detect. So you want to detect whether a particular group of data is in your training data. Of course, you don't know what's your training data. You only get the model and model output. You want to identify from the model output whether a particular piece or particular set of data is used in the training. So hopefully we can use such kind of technology to identify this AI-generated text, whether they are used in the training of new model. Then we can probably prevent using that.
So in your opinion, do you think that if we kind of split actors into two teams, defenders trying to protect this responsible use, or at least on the front of like watermarking and detection, and the attackers who are trying to subvert that, do you think one team is going to kind of win out in the long run? So for example, like with a lot of cryptography, generally speaking, if you follow best practices, your cryptography is going to be safe against most attacks. In this case, it seems maybe a lot harder to be defending. Do you think there's ever going to be, do you think the defenders are going to have enough of a head start that they're going to be able to keep ahead of attackers?
Okay, great question. So that's why we have adversary attack, where our adversary are getting smarter and smarter and stronger. Yeah, we are not bulletproof against all kinds of attack yet. As we develop better watermark, surely there will be even stronger attacks as well. So the goal here is hopefully we are improving at a faster pace, and we make it really easy to use. That most people will still be protected. But of course, there can be scams, even if you use like cryptography, right? So even if you are very careful, you can run into these kind of scams. You can, again, our watermark and this line of watermark approach can run into that issue as well. So that's why we need to team up with experts in cryptography or in security or in privacy. Well, luckily we have Scilab here. is your question like the way I'm teaching in class and the way I assign the homeworks?
Like, do you use this research in your class?
Oh.
Are you concerned that students are using ChatGPT?
Okay, that's a great question. Well, for my class, or maybe many of the class offered in SCS, I think we are not particularly concerned because our homeworks are hard. Well, it's even difficult for like experienced student to come up with a solution. But I can imagine it will be problematic for some other domain, like English or writing, or like some other domain. It might contain more issue, and surely we want to ensure this. That's why we want to make sure this kind of approach is robust to like editing. Students, you can't really prevent them from using these tools, right? You can already use Grammarly. Well, if students just use ChatGPT, well, that's my personal opinion. If students just use ChatGPT in the same way as Grammarly, you use it to like proofread and correct some grammatical error, etc. But the main idea, the main content is from the student, from the human. Then that's okay, right? And if they just use the text generated by ChatGPT out of box, okay, they didn't do any work. Our method, or this line of research, is trying to ensure that where students, if they just use it out of box, it will be easily catched. It's like you are copying other people's homework. But if we spend a lot of effort trying to modify based on this tool AI-generated text, then yes, they can evade, but they put the effort. We acknowledge that. Well, that's my personal opinion.
I wonder, do you think that the same ChatGPT model or GPT-4, do you think, in your experience, do you think that their answers are self-consistent? Actually, I have follow-up questions, but I want to hear your answer. So what's your experience?
Oh, okay. Well, I guess your question is not really about the watermark here. So your question is whether the generation is self-consistent from this large language model. That's a great question. We have a paper in submission under review to study the consistency of question answering regarding to factual knowledge. We study the statistical consistency, and we are able to quantify that. The short answer is no. In a lot of cases, we find it's inconsistent. So, meaning that if we just paraphrase a question, it will answer differently. And it will change its answer. If you just ask, are you sure? It will change the answer. They are not sure.
Actually, my example is like NP-complete. That is a very well-defined concept in computer science. But both I and my students use ChatGPT to answer is mixture integer programming is NP-complete. And we got totally different answer. One set says yes, significant blah, 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 blah. And another says no, blah, 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 blah. The same ChatGPT. So, well, this really suggests something. How do you possibly find the truth? This also suggests another thing. If we allow students to use ChatGPT to answer, to do homework or to do exams, so the way we generate questions should be focused on the questions that ChatGPT are self-inconsistent. So in that sense, the student's answer can be all over the map. It's very interesting.
I totally agree.
Do you see any utility methodology to ensure their human-generated text doesn't become part of a large language model? If somebody wants to opt out of that scraping system this way.
Excellent question. So this is actually related to an earlier question of this student wants to ensure that this AI-generated text won't be used by future training of the model. So yours is like you want to ensure a particular text written by human is not used by the model. This is belongs to one category of problem called membership detection. It's difficult. It's very challenging if you just want to detect individual piece of text, whether it's used or not. But if it's a large collection, yes, if let's say if it's all the works from Shakespeare, okay, we can probably detect, or if it's all the text from Wikipedia, we can probably detect that. But again, we need a better algorithm.
In the back corner there? In the corner? Yeah.
Thank you for the talk. I was just wondering, like, scenarios where the suspect is, say, smart enough and maybe also very used to using distillation to generate data, do you think they can, a lot of distillation procedures will involve like calibrating the student model and the teacher model, because there is a lot of evidence that distillation generally without calibration will not work. The teacher will produce either overconfident or miscalibrated like soft labels, and students will not train very properly on those. So what is the interference, or rather, what is the invariance of the detection methods if we know that a suspect is smart enough to calibrate their system, and also basically just apply calibration?
Okay, calibration. I'm not 100% sure about the type of calibration you are referring. What kind of calibration you want to add?
If the suspect uses out of distribution data to generate the student tables, and the teacher model has been trained on a completely different distribution of data, the teacher tables will not be essentially a very good fit for the student.
Okay, I see. Let me try to rephrase. So your question is, well, I can answer related, but maybe slightly different question. So if a student adversary use some data set that is not in the original domain of the teacher model, and then they use that to distill from the model, and then can we actually detect such watermark from the student model, right? So the general answer is we do have some assumption of the watermark for the distillation case. For the distillation, actually, we do assume at probing time, our probing data set belongs to the same domain of the student which they train on. So student, they can choose any domain they want to probe to distill from the original models. That's okay. And we just assume that will work. Otherwise, they won't use the student model, right? So we just assume it can adapt to the particular domain. And this signal will be carried over. But at probing time, when we want to detect such signal, we do assume that we know the domain of the student. Of course, sometimes it's difficult, but usually it's okay because you can probe the student model and see what's the output and probably guess what's the domain they are in. And then once we know that, then we can use the same domain data to probe the student model and then to detect such watermark signal. Then everything should work. Of course, if we don't know, if in some case we really don't know the domain, and it's not solved yet. I think we still need to have a better way to identify the watermark here.
Let's do it in the back.
For agents that have tool access, like access to the web, do you feel like the homomorphism?
Can you say it louder?
Yeah, for agents, like
Oh, that's an excellent question. So if we have generation cases where this has maybe limited vocabulary or maybe really strong dependency among the words, well, our assumption is on the probability of this next word token belonging to one group. So we are not assuming the probability for individual token. Of course, the individual token probability, they will change. Otherwise, you will generate the same token for every step, right? So this individual probability, they will change. But hopefully, the way we design the hash function and the way we split them, we can ensure this probability of tokens belonging to a particular group won't change too much over time. So this is our assumption. Is there any case that will violate this assumption? Yes. So I give some example. We will have examples like that. How to solve that, we don't know yet. That's a very challenging question.
Can I follow up on that? So one of these situations may be like, or I'm asking sort of, is one of these situations like when there's a big shift in the vocabulary, like if you have a natural disaster or a terrorist event, would that be a situation where the probabilities change sufficiently so that this might break?
Yeah, well, here's one example I do have. So if you have a particular way to generate something, so you really have some dependency or some secret message you want the model to generate in the end. So as you generate more and more tokens, the possibility of the token is really limited. So you are limited. So in the end, you can only generate maybe one token from the vocabulary. So really, that means that the probability of this green list or red list, they just fall into this one token probability, and you don't have other choices. So in this case, it will be difficult because you don't have other choices. Even if you add a small amount of signal here, you won't be able to bias the probability. So basically, you can't add a watermark. Or if you really want, you need to add a very large signal here, which basically will destroy the generation.
So it seems like the watermarking scheme does not depend on the sequence, which means you do have like a fixed green list for all tokens. Is that correct?
Yeah, does my watermark has a fixed green list, red list? Yes. So that's a key difference, and that's why we can get stronger theoretical guarantee.
Right. So if that's the case, it seems like the adversary can figure out that list very easily just by counting like tokens in the generated text and look for tokens that appear more frequently than they're supposed to.
Okay, the question is whether adversary can guess this green list or red list. Theoretically, yes. In practice, it's hard to get it exactly right. They can probably get most of the more frequent tokens right, but not those tokens in the long tail. And especially for those tokens with many synonyms in the vocabulary, it will be difficult. But the key point here is whether this method will be robust even if adversary knows green list or red list split. The answer, well, at least our partial answer right now is yes. Even if adversary knows the green list or red list split, we are still able to protect it because, well, here's one here's one example. Let me use this example to show. So we have a lot of green list and a very small number of red list tokens here, right? And adversary, I know all the green list words, Now what I should do? Well, I should replace many of these green list words with their probably synonyms in the red list, right? So that this probability will be more or less the same as the unwatermarked one, which is a 50-50 split. So I need to do a lot of edits here. So remember that we actually quantify the effort the adversary actually have to put in editing the text. So in order to evade, they actually need to change almost half of the tokens, half of the words here. So that's the guarantee we can provide. So even if the student, even if the adversary, they know this, if they try to evade, they still need to put a lot of effort.
One last question.
Yes. Hi, thank you so much for your talk. In the beginning of your talk, you actually mentioned the privacy part, where there is a lot of personal information that has been trained in the training data itself. So have you done any work like mining the watermarking with differential privacy? And I would like to know how you actually preserve privacy in the process.
Okay, the question is how we protect the privacy of user or data from during this training of large language model. So this is one topic I didn't cover in this talk, but we do have some work on that. And yes, we found some real cases that even if you train the model from public domain, it can unintentionally memorize some sensitive information. So the way to protect that is, as you mentioned, we use differential privacy, but we modify the differential privacy in a way so that we can actually protect the content rather than every words from the vocabulary. We don't want to protect every words. We only want to protect those entity names, phone number, or email address, or social security number, etc. And we have some theoretical algorithm that can, some algorithm can provide a theoretical guarantee with respect to differential privacy.
All right, let's thank the speaker again. We're